Good morning, everyone, and welcome back to day 2. I will be your chair. I'm Daniele Rogantini, postdoc here at the HETG group of Chandra of MIT. And today we start with diffuse gases and emission. I will try to be very strict with time, so we have enough time for coffee and lunch. And the first speaker, invited speaker of today is Irina, which will talk about high resolution X-ray spectroscopy of galaxies, cluster groups, and massive galaxies.
Good morning, everyone. Thank you for showing up early for this talk. So we switch into diffuse emission in this session, and I was asked to review high resolution X-ray spectroscopy in clusters, groups, and massive galaxies. So we'll be talking about hot volume filling gas that is emitting X-ray mainly through Bremsstrahlung and emission lines caused by electron collisions, right? So when we talk about clusters, the emission will be dominated by iron K lines. It's pretty hot gas component. When I talk about galaxies and groups, it's mainly dominated by iron L, right? Other than that, there is not much difference between both. So frankly, there is not much high resolution spectra yet. We have very bright future. Everyone saw the XRISM will be launched very soon, and bright future very soon in 23 days, if I calculated correctly. So this is the launch date, which will be August 25th, Friday here night. So please celebrate, fingers crossed, things will go smoothly. So the mission is designed to basically look at extended sources with high resolution X-ray spectral capabilities. So hopefully a year from now, we'll have way more data to talk about. Will be super exciting. So what we have right now, so probably the best spectrum is the one we got from Hitomi. It observed the core of the Perseus cluster. Over there, you can see, so you have to see my cursor. So this is the center of the Perseus cluster. 230 kiloseconds, relatively short observation, but we've got a lot of information. I will show in the next few slides what we learned from the spectrum. This is how it looks. We beautifully resolved all the emission lines and found the best fitting model that was basically one temperature, 4 keV gas in C, collision ionization equilibrium with a bunch of corrections for galactic absorption, resonance scattering, agent contribution, charge exchange. We were able to find a pretty good model that describes the entire spectrum from basically 2 to 8.5 keV. That looks nice, beautiful. What have we learned from that? Let me just quickly review a few results from Hitomi works. So first we measured velocities, right? Obvious thing you can do, you can measure line broadening shifts, and you can get dynamics of the gas in the region that is dominated by agent feedback physics. This is the maps we've got. So you can look typical values, 100 to 100 kilometers per second, translate into Mach number about 0.3, 0.45. So we are in subsonic regime as expected, but compressive effects could be already, starting showing up. In terms of pressure, the ratio of turbulent to thermal pressure is about 5 to 10, 11%, depending on how you calculate that. This number is important, particularly for precise cluster measurements in cluster cosmology. So we see that at least central regions are relatively relaxed. We can apply hydrostatic equilibrium here. What else we learned? We learned that injection scale of these motions, we couldn't have very strong constraints. We have just one pointing, but we found it below a few hundred kiloparsecs, which is also consistent with the picture when feedback is driving all these, motions of the gas. And what we also looked, we didn't find any deviations from Gaussianity, right? So we looked at the spectra, shape of a spectra. You may expect that because of superposition along the line of sight, there could be some deviations from Gaussianity. Well, we didn't see any, right? So it simplifies our life. That's what we got from velocities. The next thing I wanted to highlight is resonance scattering, also mentioned a few times in this conference. So clusters are optically thin, except for a few optically thick resonant lines, and that scattering can occur. This is my schematic view of what is happening. So basically, photons will be leaving line of sight or reaching, depending on how you look at. And we can model that, right? So we can take a model of a galaxy cluster, typical, and we can run radiative transform, Monte Carlo simulations, and see what distortions in the spectrum will be produced. And here I'm just highlighting work I was doing back in 2013, where we basically did Monte Carlo simulations of this process. And we found that indeed, if you look at the core of a Perseus cluster, for example, resonance scattering will cause a suppression of a flux in the strongest 6.7 keV line. So these results, like orange and red, correspond to Mach number 0, so there are no motions. But we know if there are motions of gas, they will be basically reducing the probability of scattering. So effect will be still there, but it will be much less strong, right? So these black and purple correspond to Mach number 0.5 with and without resonance scattering. So from here, you can also see that we can use in principle resonance scattering to put constraints on velocities, right? In addition to Doppler broadening. So I was very happy to see that indeed Hitomi showed that there is resonance scattering in the core Perseus cluster as we predicted. So we took the spectrum from the innermost part of Perseus where we expect this effect being the strongest. This is the spectrum we've got. So this is helium-like triplet, W resonant line, and whatever we're doing trying to model this spectrum, we basically concluded that the flux in this line is suppressed. And in fact, our best fitting optically thin model systematically overshots, basically overpredicts the flux in the W line. So there is clearly suppression, approximately factor 1.3. So resonance scattering was present there. Now the question, what do we do with it? Well, we can measure basically velocities using the same diagnostics we just now looked at. All we need to do is to measure flux ratio, like basically optically thick line to optically thin lines and compare with predictions from modeling. So here I just highlight in result for different line ratios. You can just focus on the top solid line over here that shows the ratio for W over Z lines. Sorry, there is a delay in cursor. We can find that the most probable value of velocity is about 150 kilometers per second, although the uncertainties are quite large, mainly coming from the uncertainties of measured line ratios. And it seems to be consistent with Doppler broadening, right? So this is what we've got from the same region for sigma, just looking at line broadening. Nice, both are consistent. Are we expecting that they will be consistent? Well, it depends, because we know that, for example, if there is any anisotropy of motions, it will be very differently imprinted on resonance scattering and Doppler broadening. So in principle, we may expect that these values will be different. We also know that the resonance scattering is mainly sensitive to very small scale motions along the line of sight, while Doppler broadening could be both due to small scale motions or superposition of bulk velocities along the line of sight, right? So if we see any differences, this could also tell us something about the scale of motion. The fact that we see values right now sort of similar to each other, very close to each other, tells us that probably we are dominated by small scale motions. However, I'm looking forward to get data from XRISM, from XRISM to reduce this uncertainty, right, and start hopefully seeing some differences between both methods. So that will be exciting diagnostics for velocities. All right, what next? Well, I wanted to quickly highlight charge exchange. We didn't detect it, but we do see very convincing hints that it's present there, and it's never been detected in clusters or galaxies. So we know that in the course of many clusters, in particular in Perseus, there is also coal gas. So this is famous image in color shown H alpha emission. So these are famous filaments. So there are different gas phases, and they may interact with each other through charge exchange. And as a result of that, we expect that there will be very high flux of high-end transitions, and they will appear as little bumps in the spectrum, right? And we did see that there is bump over here, so there are some bumps over here, but the significance is about 1.5, 2.5 sigma. Not yet quite there. We need more data. Again, XRISM will give us more data, but looks very promising. All right. So charge exchange will be an exciting process we will study in very soon. Another thing I wanted to highlight is temperature diagnostics. That's also kind of non-trivial, not very commonly done. I mean, yet we don't have data for that in cluster community and also in galaxy communities, basically looking at different temperatures, right? So usually we are measuring just continuum, we're looking at electron temperature, but we can also look at excitation or ionization temperatures, right? By looking at a line ratio. So excitation temperature, as you know, it reflects kinetic temperature of free electrons in this hot plasma. And we can trace it if you measure the ratio of lines from the same ion. And ionization temperature basically shows ion fraction, and we can measure it by looking at the line ratio from different ionization states. And if all of these three temperatures are kind of equal, that means that we are dealing with a single temperature, optically thin C plasma, right? And if you see any deviation, then there is something more interesting happening. So we extracted spectra from the central part, nebular, and the outer parts, which I show here in the bottom. And y-axis temperature, x-axis different line ratios, tracing excitation temperature or ionization temperature. And I would like to pay attention on this figure over here, where we clearly see that ionization temperature is increasing with atomic number. So this indicates that this simple model doesn't really work here. And in fact, we saw that in this inner region, basically there are two temperature components, 3 and 5 keV together give us like kind of 4 keV gas, what we saw with a global single temperature model. So it looks interesting, right? And we don't see any indications of that in the outer regions. So hopefully we'll do again even more fine diagnostics with XRISM, especially given that we will have soft X-ray spectra, like soft X-ray line present in our spectrum as well. So we'll be really excited to extend this work. So besides temperatures, I wanted to highlight, say a few words about chemical composition. Now that we're resolving all the lines, we can do it very beautifully. And I wanted to highlight work by Aurora Simonescu. So basically, she combined hitomi and RGS data and measured the ratio of all these elements on the x-axis to the iron abundance. This is the best measurement, with including systematic errors that are shown with the with this region on the background. And one of the main questions we wanted to answer is here how well our current supernova yield calculations actually reproduce this observed abundance pattern. And one of the main takeaway messages from this work was that there are actually challenges to reproduce this abundance pattern with a linear combination of supernova nucleosynthesis calculations that exist today. In particular, there are challenges in describing these intermediate alpha elements. And there was a discussion that probably we need to include some additional physics like neutrino physics when we are calculating supernova core collapse yields. So also interesting new insights. And again, we'll have more information with XRISM. Finally, last work that I wanted to highlight, if you're not yet convinced that this is a very powerful data set, the last thing I want to say is put some constraints on supernova type 1a progenitors. There is a simple prediction that we can test. Basically, we are saying that the abundance of iron peak elements, these in particular, they are tracing how the progenitors of this supernova type 1a evolve and explode. And this is theoretical prediction over here that shows abundance ratio of these three elements relative to iron. And the shaded regions on the background show basically different predictions. So the blue one, this is a situation when we have delayed detonation near Chandra X-ray white dwarf, plus contribution from core collapse supernova. The gray one, this is basically a single sub Chandra X-ray white dwarf, plus contribution from core collapse supernova. Red one is a mix of both. Well, we can read more about this in the paper, but the takeaway point here is that our measurements, observations from hitomi that are shown with the black here, are basically saying that these iron peak elements can be only explained if you have a combination of near Chandra X-ray and sub Chandra X-ray white dwarfs in our supernova type 1a progenitors. All right, so looks exciting. And again, a reminder, this was just 1 point in 230 kiloseconds, right, in the core of a Perseus cluster, right? So I'm really looking forward to see what we'll do with XRISM. So before we go into XRISM, I also wanted to spend a couple of slides, since this is kind of a review talk, to highlight work from XM Newton and RGS observations. Sure, we're dealing with extended sources, but there are compact bright regions in some of the systems, in particular if we're talking about elliptical galaxies and groups. This is a famous example of NGC 4636. You see very bright core. So we can actually use RGS and get some high resolution spectra that are shown here on this figure. And I, in particular, wanted to highlight this CHEER sample that was developed at ESRON by Jelle de Plaar and others. So basically, this is a pretty powerful sample of about, I think, 50 bright galaxy clusters, well, mainly elliptical galaxies and groups. All the systems, they have very bright oxygen 8 lines that could be clearly detected. So using this sample, people have done some interesting studies here, just highlighting very quickly some of the works. So Jelle de Plaar in 2017 measured very accurate abundance measurements of oxygen and iron and show that they're basically independent of temperature. And basically, the main conclusion is that very likely this is because enrichment took place before the intracluster medium was actually formed. So an important conclusion. Francois Mernier actually measured average radial profiles of many elements shown here, and just iron average profile shown here, separate for clusters and for groups. So that was a very new, insightful result. Beside abundances, people tried to measure velocities, of course, and here I'm just highlighting work of Ciro Pinta, who tried to measure Doppler broadening of velocities and constrained upper limits of about 500 kilometers per second for about half objects in the sample. And there were some objects that show very high upper limits, like will be higher than 1,000 kilometers per second, which will be very interesting. It will be interesting to follow up with XRISM. And finally, work by Anna Gajavik, who combined actually Doppler broadening and resonance scattering velocity measurements for a subsample of objects in this CHEER sample, and she was able to obtain actually very well constrained velocities in all these objects listed here, and found that within this inner few kiloparsec region in these bright ellipticals, typical velocity is about 100 kilometers per second. All right. So that's a very quick review of what we have done. I mean, people have done more, of course. This is just some of the highlights. Now let's talk about future. I think I'm doing good in time. So future, Bright, XRISM, and Brian Williams will talk more about it in the last day of the conference. So I'm not going to talk about the status of the mission, but I wanted to very quickly highlight what kind of extended diffuse sources Extragalactic will be observing during the first 6 months of the mission. So during the performance verification stage. Not going to say much, but if there is any of your favorite objects, please just come and talk to me. I'm happy to share more information. But just to give you a flavor of what we're going to be busy with. So first, we propose to observe the core of the Virgo cluster, or M87. This is the closest cluster to us. It has very strong agent feedback indications right in the center, and we basically want to study this agent feedback both spatially and spectrally resolved. So we want to have these 4 pointing observations, about 500 kiloseconds in total. And this is kind of simulated spectrum we expect, and you can clearly see that we can nicely decompose hot and cold components and basically look at dynamical coupling of different gas phases, right? So for the first time, really exciting. So we will look at mixing of different gas phases in this pointing. We look at gas dynamics and metallicity is very close to the supermassive black hole right in the center. And we will study these things in a relatively quiescent region, although we have to keep in mind that there is shock over here. So strictly speaking, we'll be looking at turbulence upstream and downstream the shock as well. Right, so that's what we're going to do. The next one is Perseus, of course. Well, Hitomi only looked at the center here, so the sine squares show what Hitomi observed, but we want to do a set of observations along the radial direction over here. Kind of one of the primary goals is basically to look at this transition between the region, which is dominated by agent feedback physics, to the physics driven by structure formation by mergers. So the outer 2 pointings are basically driven by dynamics driven by mergers, while the inner region is affected by agent feedback. And besides turbulence, we'll be able to measure abundances with the precision of a few % only. So this is looking very exciting, and detect rare elements, including aluminum and natrium. So that's Perseus. Finally, we want to look at smaller mass systems, NGC 4636, the one I showed a few slides before. This is one of the brightest galaxies. It's also dominated by agent feedback physics right in the center. So we want to have central point in about 100 kiloseconds. And kind of combining all these 3 objects together, we basically want to look at the physics of agent feedback as a function of halo mass, right? So Perseus will be the most heavy component, NGC 4636 will be the lowest mass component, right? So that would be our big goal here. So besides physics of feedback, we want to look at also abundances, and particularly want to look at Centaurus cluster because it has very weird, very strange abundance pattern. We have measured from the CCD data that this is how abundance profile looks like. It's extremely peaked value about 1.5 solar at 10 kiloparsecs, and then there is a sharp drop towards the center. So we don't know if this sharp drop is produced by depletion of metals, or it's just a fact that we basically multi-temperature effect that we cannot recover from current data. We don't know. Well, with 250 kilosecond, this offset pointing with XRISM, we will basically measure all of that, basically probe both inner region and is the peak of the abundance pattern. All right, a couple of more slides, a couple of more targets that we'll be looking. Coma cluster, non-cool core cluster, no agent feedback. Here we want to look at this textbook example of turbulence and hopefully measure turbulent cascade. So not only velocity amplitudes, but also associated scales. Ask me more if you want to know, how exactly we're going to do that. And a couple of other objects, Able 2029. So Eric Miller will talk about it. This is mainly cluster for cosmology. We'll be looking at velocities all the way to R2500. So basically perform a set of observations along the vertical direction. And Able 3667, this is another interesting object that is going through merger, and we want to reveal the geometry of a merger, whether it's caused by sloshing or stripping. So we'll perform this observation, measure velocities inside the cold front, and directly use this to kind of narrow down the model and use it as, for microphysical studies, in particular, putting constraints on gas viscosity. All right. Finally, 2 other things I wanted to highlight. If you go scales from clusters to galaxies, we also want to look at more regular galaxies, in particular M82, the famous galaxy. I'm sure you've seen this picture many times. This is a Chandra view of this galaxy. So we'll look at the central part with 50 kiloseconds. And the goal here is to measure velocities of outflows. Basically, we want to understand whether the wind speed exceeds the escape velocity. And we also want to understand what is actually driving this wind, so wind mechanism. And finally, if there is enough time during the PVFS, we also want to look at the typical bright spiral galaxy, in particular M51, and measure emission, measure distribution in elliptical galaxy pretty much for the first time. And this is the point in where we are proposing to look both at the nucleus of the spiral galaxy and looking at the beginning, basically, of the spiral pattern. So looks exciting, right? This is a very ambitious program. And stay tuned, will be data coming, and of course there will be hopefully even more science through the GEO part of the mission. Now, all right, so that's what I covered so far. So we looked at what we can do today with Hitomi and RGS, bright future with XRISM, but now let's also spend 5 minutes to talk about even more distant future, because I think it looks even more exciting. So in the past year and a half, we were together with a huge collaboration. We were working with a number of people here at CFA at NASA, basically proposing this line emission mapper. This is a mission concept for the NASA 2023 astrophysics probe. So the mission is basically designed to study very faint and extended X-ray sources with a microcalorimeter resolution, right? And we are looking at relatively soft band from 0.2 to 2 keV. So the key characteristics are field of view 30 by 30 arc minutes with 15 arcsecond pixels, resolution about 1 or 2 eV. So in the central subarray 1 eV, and in the rest of the array 2 eV. And we'll be dealing with relatively soft X-rays. So here you kind of see where LEM stands compared to other missions that we will have high resolution spectral capabilities. So why soft band? Why do we need higher spectral resolution? Well, you probably know that in soft X-rays, we are mainly dominated by emission from our own Milky Way galaxy. And in order to get collected data from other sources, we need to have high spectral resolution, right? And this figure illustrates why. Right, so this is the typical spectrum that we simulated for hot halos around regular galaxies. And the spectrum that we'll get will be a combination of this red and purple. Purple component is coming from the Milky Way, and the red one is coming from the actual galaxy. So if you select it in the right redshift, basically all the emission lines from the galaxy will be redshifted compared to the Milky Way emission, and we'll be able to resolve that. Obviously, we cannot do that with the CCD resolution that is shown here with a green curve over, right? We just need resolution to actually do this work really well. Well, that looks exciting, looks promising. So with these LEM capabilities will be basically one of the primary goals is to map this CGM emission, circumgalactic medium around the galaxies, and also look at IGM, intergalactic medium, basically clusters, cluster outskirts, and also cosmic filaments. And this is in line with one of the Astro 2020 decadal survey discovery areas. So let me talk a little bit more what we can actually do with CGM. So mapping CGM with LEM. First, a bit of motivation why we need to do that. We know that galaxies are not just small optical images, even though all theory of galaxy formation was mainly built on optical data. But we know that galaxies are actually very much more. And this is a classical picture from the CGM review from back 2017 that shows the kind of artist impression of how galaxies are actually complicated. So we have continuous flows of matter. There is accretion of gas, and there are massive outflows. So the galaxies are very complicated, and this is mainly driven by feedback processes and accretion. So we want to resolve all of that. So why do we need soft X-rays for that? Well, if we take a Milky Way mass galaxy and even more massive galaxies, we will actually see, we can kind of predict what is the mass fraction in different kind of emission lines that we will detect. And we see that for Milky Way type galaxies at large radii, most of the emission is actually coming from oxygen 7 and oxygen 8 lines, which are detected in soft X-rays. So with soft X-rays, we can basically map the most massive component of this CGM in a Milky Way type mass galaxy. And why we're interested in why we're interested in outskirts of the CGM? Well, multiple reasons, but one of them I wanted to show here. This is a recent result coming from, basically comparing state-of-the-art cosmological simulations, illustrious TNG, Eagle, and Simba, that are basically predicting what will be the surface brightness in these lines for these galaxies, and it shows radial profiles. And we do see that the inner region, kind of our simulations, kind of are consistent with each other. However, as we go to the outskirts of galaxies, the discrepancies are becoming bigger and bigger. So we basically don't know much about the outer parts of the CGM, and this is exactly what we can trace with LEM again in the Milky Way mass galaxies. So now let's see what LEM can actually do. Let's take a typical Milky Way type galaxy at this redshift from illustrative simulations. This is how it looks in the optical light, and the dashed line here, dashed circle, shows R500. So basically outer parts of the CGM. So this is what we have right now, and this is what our current galaxy formation evolution models are built on. Now we have LEM. Assume we have LEM, we have 1 megasecond observation. We get this beautiful spectrum. We were able to decompose Milky Way from the CGM emission. Now let's look at the look at these very narrow bands images around oxygen 8 and iron lines over here. So this is how exactly the same galaxy would look like, the same circle. And you do see that in these lines, finally, this galaxy is actually shining, and they have emission all the way to R500, right? And even beyond. So that tells us how powerful LEM would be. We will finally be looking at the most massive component of galaxies for the first time with this type of mission. And again, to illustrate why we cannot do it with CCD, this is similar kind of simulations of the same galaxy, but now we're using CCD type of resolution, and we do see that basically we can gain something right in the center, but overall our emission will be dominated by the background, which is basically Milky Way background plus point sources. All right, so hopefully I convinced you that that will be exciting. What we can do with this data? Well, I'm not going to talk much. There will be talk about ZuHone later today, but we're basically looking at all these kinematics of outflows and inflows and related AG and feedback physics, right? Stay tuned, there will be more about this, and I will move forward. In the last 2 minutes, I also wanted to highlight cluster science. So we'll be doing a lot about clusters with XRISM, but we'll be mainly focusing on central, very bright regions where we get most of the photons. However, there is the whole, other dimension, right? Basically, when we go to the cluster outskirts and even outside of the virialized radio, there is actually a lot of interesting physics, which is very poorly constrained with simulations, and obviously we don't have access through observations right now. So what we're going to see with LEM? Well, this is just basically cosmic web where we find in the center cluster of galaxy. We zoom in one of the clusters, and we just do pointing observations with LEM, trying to cover all the central area, R200, and even beyond R200. And then we try to recover basic characteristics such as gas kinematics and chemical composition, and see whether LEM can actually recover the true values, right, that we get from simulations. So results are shown on this figure. This is velocity dispersion as a function of radius. You can look at the red points and compare them with theoretical predictions shown with the shaded regions on the background. And you do see that we can beautifully recover all the velocity to all the way R200 and even going beyond virialized regions. This is basically regions where we have the situation when cosmic flow gas is actually interacting with the galaxy clusters and trying to get thermalized and virialized, right? So very, very interesting sort of regime in hollow formation. When it comes to metallicities, we can also recover pretty well the observed ones, well, the true ones, right? So the red points are observations with LEM, and the orange curve is what we actually know from simulations. So it looks pretty powerful, right? So we can recover all this information from the central parts all the way to outskirts. And this is just a list of questions, incomplete, that we'll be able to address once we have this data, basically looking at when and how the AGM was enriched, what types of stars enriched that, and how the flows of matter along the cosmic web filaments actually get virialized and thermalized in clusters. Finally, last slide, we can also look at cosmic web. Given that the LEM has a very large field of view, we can do it pretty efficiently. Again, we don't need crazy exposures for that. And here I just show again mock LEM spectrum from the cosmic web, taken from illustrative stingy simulations. And the trick is very similar to CGM, right? We want to detect the filaments at specific redshift so that we can kind of distinguish between Milky Way and emission from the filament. And these red bumps over here are related to the cosmic web emission, and we want to basically the ultimate goal here would be to see how we can probe the kind of how metals from the galaxies were ejected into the cosmic web, right? So we want to basically answer the question whether galaxies have been proficient chemical polluters of the cosmic web or not. And again, it's also related to the feedback physics. All right, there will be talk by Ralph Clough later tomorrow, I think, who will talk more about LEM, and also any other geoscience unrelated to these sources will be covered there. With that, I'll leave you with my summary. Not going to read through exciting results from RGS and Hitomi. Even more we have with XRISM. Some of the immediate things we'll be looking at listed here, and possible exciting even more distant future with LEM. Thank you.
Thank you, Irina, for this great talk. Questions? Everything.
I have a question on the LEM simulations that you showed. They were all based on TNG, but then if you go back to the motivation
well, I don't know what to leave here.
slide, I mean the simulations, the different simulation, Eagle,
Oh, yeah.
Simba, and that is by far the most promising, no? So the question is, what if the situation is the one
Yeah, please
you
refer
get
to
10
this.
times less car.
Look at this paper that we just submitted, where we actually look at all type of simulations, including Simba and everything. I just picked for TNG for the purpose of, of this talk, but we do understand this problem, and we do look at LEM predictions for all kind of simulations, and basically design an instrument to make sure that even these weak signals could be detected. Yes.
And what is why do they differ so much? Is feedback?
Very good question. Very good question. We don't know. So there is different implementation of agent feedback physics, but these are also very different type of simulations. They have very different numerical prescriptions. Frankly, we don't know. Yeah.
Okay, thanks.
A question about resonance scattering part. There's also a question on the chat from Mark about the column densities you need for the iron 25 resonance scattering in the W line. My question is very related. It's basically, I mean, as I commented already twice yesterday, when you scatter a photon, the photon doesn't disappear. It goes somewhere. I mean, we don't release people from jail because they go somewhere else. So, right. So these photons, where do they go? And how many photons are scattered into the line of sight, right? You may have that, which are scattered away somewhere else. Yeah. But you're deriving a velocity here from that.
Exactly.
That's related to that. So are you assuming that these are all the photons that disappear?
We're doing proper Monte Carlo simulations, which are very time-consuming, not something you can easily do on your laptop. So we input the model of a cluster, I don't know, radial distribution of density, temperature, abundances, accounting for systematic uncertainties and all of that. And then you run full Monte Carlo simulations. Yeah. So you trace individual photons where they're going, and you randomly redistributing them, and then you can make assumptions about the velocity field. Sure, we don't know the details of the velocity field, so right now we are characterizing it with one characteristic velocity, whatever it means, but that's kind of, we try to understand the bulk effect of the velocity, right? So yes, you do proper Monte Carlo simulation. I mean, they're not complicated. Yeah. And remember, optical depths here are like 1, 2, 3, so it's not like 10. Yeah. So it's still pretty doable. Okay. Yeah.
Well, resonance, otherwise they're completely different.
Yes, and then going back to your question about emission,
about the geometry as well.
Right. So exactly. So we are dealing with a spherically symmetrical geometry, but when I was applying this to relaxed clusters taken from cosmological simulations where I have true geometry and approximated in with spherically symmetrical model, the differences were, this was not the main source of uncertainty. The main source of uncertainty was coming to atomic data and our emissivity models and all of that. So I do not worry about it yet, because we have like elephant in the room to worry about atomic data. But once we solve that, yes, at some point we'll be dominated by the systematics too, not at this stage. And about the increased emission, if we actually go to cluster outskirts, the effect is reversed, exactly what you were saying before, right? We start seeing the opposite, yeah. And it really depends on the system, how the surface brightness looks like, you know, there is no one answer for everyone.
Spherically, you wouldn't see anything.
Yes, exactly. Yeah. Well,
yes. Okay.
Yeah.
Not just one region here, so we actually did see in the center the effect was the strongest.
Exactly.
But it goes away already.
So yeah, if you look at the spectrum and this outer observation of OVII, basically the effect disappears. It gets weaker and weaker. Yeah.
It's an amazing discussion, but you have to move on. Thanks a lot, Irina. Lydia. Irina.
Oh, sorry. Yes, I took.
Next talk is from Lydia. She tells us about observation of warm-hot intergalactic medium in oxygen 7, oxygen 8 absorption against diffuse extended sources with Athena and LEM.
Long one. Okay. Hello, everyone. So as Daniela mentioned, I'm Lydia Stofanova, and I'll be presenting you the results of my upcoming paper that is soon to be submitted, very soon, so stay tuned. And this is the work that I have done as a part of my PhD under the supervision of Aurora Simonescu, Jelle Castra, and Joop Shea. So I thought it would be nice to start with showing you a picture from the cosmological hydrodynamical simulations. These in particular are called EAGLE. And here you can see how the simulations are showing us how our universe probably looks like on very large scales. And here you can see in these very bright blobs, these are probably the places where you would find galaxy clusters. So it's no most massive gravitationally bound structures in our universe. And here exactly just going back to what we discussed, these bright blobs, you can exactly see the AGN feedback there happening. And as you can see, there is actually way more than just these galaxy clusters. So there are these filamentary structures that seem to be connecting them. These are what we also call the cosmic wave filaments, which, as I often say, are acting as a feeding pathways through which the galaxy clusters can accrete more matter. And of course, as we know from the cosmic microwave background, this is not how our universe looked like. It was more homogeneous, and over time, the gravity played a role, and more massive objects started forming in our universe, as for example, as I said, the galaxy clusters. And of course, today I have very limited time, so I just will be focusing only on the cosmic wave filaments. And from simulations, we know that this is very diffuse and very low density gas that is quite hot, so very ionized. The temperatures, as you can see, are between 10 to the 5 and to 10 to the 7 Kelvin. And there's this consensus, as Irina, where did she disappear? Where as she mentioned, there is way more, and the consensus says basically that, and we could have discussions about it, and I'm fully aware of that, that the lower density gas in these filaments is called warm hot intergalactic medium, and the denser parts that is actually locked in the galaxy cluster halos, that is what we call the circumgalactic medium. I will be focusing on the warm hot intergalactic medium today. And from observations, or there are many ways how we've been trying to hunt for these, for detecting the gas in these filaments. And we have multiple experts in this room who have been trying to do so. The first one is in emission. I won't have time to talk about that, but I refer you to papers and many more that discuss how we try to hunt for these filaments in emission. And then another one is the absorption, where we have like basically two methods that we try to hunt for these filaments. So the first one is when you try to look for them in absorption against very bright point-like sources. So for example, blazars, quasars, and I refer to Fabrizio's review paper, where you can find many different examples of that. And all the detections that we have, which I must admit that for now are with quite some lower significance. So it's still very difficult for us to hunt for them. And another one was actually proposed by Maxim Markovic, and I had the pleasure to actually present it to him last week. And Aurora Simonescu with Ciro Pinto followed up on this another method, which is basically an idea for future missions that maybe we could see these cosmic wave filaments in absorption against extended sources. And those are, for example, the perfect sources for that are cool-cold clusters. And that is exactly what my talk will be about and what my paper is dealing with. Some of you saw very preliminary results in Barcelona. Now the paper is done. So I'm very happy about that. And I just thought that maybe with some sort of a map, I can show you the main methods of the paper and also the results. So basically what we needed to do was, since I mentioned we don't have yet many observations to study this type of physics, we needed to go to cosmological hydrodynamical simulations. So for these, we selected the ones that are called hydrangea, and I will of course explain why we selected those. These are the zoom-in simulations, as simulation people call it. These are based on EAGLE, and there were a couple of reasons why we selected those. So one of them is, for example, the fact that They provide us with around 30 galaxy clusters. And the amazing thing about them is that they are simulated up to quite big distances, so up to 10 times virial radius. So not yet something that we could observe. And the resolution is really nice. For those who work with simulations, around 10 to the 6 solar masses for the gas particles. And as you can see, these are quite massive clusters, so between 10 to the 14 to 10 to the 15.4 solar masses. Then what we did was that we went to the amazing program Spec Wizard. Older version of it is still written in Fortran. However, there is a person who managed to create a Python version. It's not yet public, but it will be soon, and it's an amazing tool. And for those of you who work with simulations, as you know, it's not very simple to create absorption profiles or create some observational predictions from the simulations. This tool does that for you when it comes to absorption. And basically, it creates the absorption profile in your chosen lines of sight. So we did that. And we basically took these approximately 30 clusters and we scanned them in different directions in the simulations. And we created the OVII column density maps just to have an idea where we could have a look at warm, hot intergalactic medium and where we could have significant enough absorption so that maybe in future we can observe these filaments. So that's what you can see right here. And maybe we can focus only on the graph that actually has axes, but all of them have the same one, same color bar. So you can see that the color bar just shows the OVII column densities. And just for your reference, this is like the circle of 300 kiloparsec. Again, I won't have time to go into details, but in the paper, we say how big of a circle we took for the extraction of the absorption profiles. And then we went to specs because one thing that you should know about simulations as well is that unfortunately for now, they are not yet very able to reproduce the cool core clusters. So what we needed to do, we went to Viklinin profiles and we took a sample of galaxy clusters with different redshifts, of course, and we simulated their spectra using specs. And then we selected our missions that we want to predict it for. And of course, for that, the perfect candidates were Athena and LEM, which are microcalorimeters. And as you heard from the previous talk, and you will hear more about them also later on or tomorrow, I won't go into too many details, but I think that they are quite remarkable, both of them. And that's mainly because of the fact that they are promising to carry the microcalorimeters, which for this type of science, they are the best because of their spectral resolution, but also because of how big the field of view is. And this is one of the main results that I wanted to show you today. So what you can see right here is the predicted spectrum that we present in my paper. So as I mentioned, and if we go back, we needed to select galaxy clusters, in particular cool core clusters that are bright enough in their centers. This is a beautiful Chandra image. And for this particular case, we selected, like, for example, that I'm showing here, Able 3A3. And this served as a background extended galaxy cluster or like extended source of light for our science. And what we then did was that we took the absorption profile that I told you about that we got from hydrangea simulations, and we put them on those and just simulated what Athena in this particular case would see. So as you can see, this is just one of the absorption profiles out of those 16. This is actually, and I must admit, this is the one that is the more promising one, which is quite, which shows us quite deep absorption. And what is remarkable here is that we kind of didn't expect it at first hand, but we saw that we could get in 250 kiloseconds 8 sigma detection, which with simple math, you can see that the 5 sigma detection could be possible in 100 kiloseconds. And of course, I admit, and you need to know, we did take into account galactic absorption and the more complex model. And for those of you who want to know more, we can discuss it later. And then, of course, I cannot go not showing line emission mapper results as well, which I see your face. The spectral resolution says it all. And why I show this example, and of course, we have multiple different examples with multiple redshifts in my paper, is because due to the spectral resolution, if everything goes well with line emission mapper, and if we still have important people like also Joanna working on galactic absorption, we could potentially even see the O7 lines that can be hidden in the forest of oxygen lines from our own galaxy. I know we can have discussions about that. However, this is basically just, and I would like to show you the conclusions that this is just another, hopefully independent way how maybe with future we can search for warm hot intergalactic medium and the detections from them from it. And as you probably saw in the title of my talk, I also promised showing you OVIII results, but I thought it would be more fun to just tell you that maybe we can discuss it later during coffee break. I do have the plots, but I thought that maybe, yeah, we can discuss it, or you can stay tuned for soon to be submitted paper. And if I may leave you with conclusions 2.0, I'm also finishing my PhD soon in the end of this year, and I'm open to opportunities. So if you want to speak to me about the science that I did, if you're looking for postdocs, or if you have any advice for young career researchers, please let me know and I'll finish it. Thank you.
Thank you, Lydia, for this very clear talk. Questions?
I knew. Who was first?
Very interesting idea, but compared to the background point like source, now you use like a cool core clusters. So you need to consider the emission, right? So from the absorber itself.
Yeah.
So how to disentangle the contribution which from emission, which kind of compensates some of the absorption. So
yeah.
A little bit complicated.
Yeah,
so,
it is.
Yeah.
And I must admit, that's the only thing that I'm very fully aware of, but we didn't have time to go into too many details. If you're talking about emission from the cosmic wave filament itself, we did have a look in whether, for example, the emission from the cluster itself in OVIII or in O7 can contaminate the results. But from the absorber, I must admit that I didn't have time to have a look at it. Of course, I noticed Irina's slides and the emission that they predicted from LEM and saw the lines. I am aware of emission studies that are coming from Eagle simulations. However, Nastasia Viers had a look on that, but I did not have a look how this could maybe ruin the science. But we did, yeah, I know. That's okay. It's a fair question. It's a fair question. I did think about it, and if I'm being honest, if I have time before I finish my PhD, I would like to have a look, because I think that the people at the defense committee will ask that. Well, it's not yet submitted. Maybe you will.
If I can follow up on this, I think what were the redshift of those absorbers? Because I think these are filaments with density of 10 to the minus 5, 10 to the minus 6 perhaps. The emissivity is way too low.
Yeah.
Way too low. I mean, and those redshifts you cannot see them with LEM.
Maybe I'll just show you first. I should have a table, but I thought that.
But
sorry. Shall I follow up?
So this is my impression. No. I just have the feeling that at those redshifts and with those densities of, if there is a CGM, yes.
Also,
So
you are looking down to filaments very close to cluster. Density has to be high.
well, this I don't. Is it at the same redshift of the cluster?
That's the thing, that we basically took the full 10 times R200 of the simulations. So the interesting thing that we were also, and that's why we were very happy that we did the science, that I also have the profile, but I don't know whether now I should follow up on this or whether Fabrizio had another question. But for example, is this the plot? No, I have it somewhere else. We did have a look at the velocities as well in the simulations. And what was, I'm sorry, I don't know whether it's there. Is it the end? Oh, okay. I can also show you, the interesting thing was that these very deep absorbers, oh, here. So the, I was quicker. So these quite deep absorbers, and I point you here because I didn't tell you about OVIII, but what we didn't know before we actually had a look and mapped these filaments was that the velocities, the total velocities are around, like of those deep absorbers, around 1,000 kilometers per second. So that is quite enough to have some distinguishing between the lines. And for example, and spoiler, also for OVIII, not with Athena, but with LEM, this actually plays in our favor, because then you can see a bit of the depletion that is placed next to the very bright OVIII line. But Fabrice, you had a question?
No, it seems that you have a very busy coffee break.
Okay.
So, but we have to move on. Next one, and the mic.
Oh, yeah.
It will be a flash talk from Majidul, which will be about spiral-like features in galaxy cluster driven by AGN jet. It's recorded, so enjoy it. We have a change in the schedule. The next talk will be Eric Miller about galaxy cluster cosmology with XRISM.
2 minutes? Okay, 2 minutes after. We'll figure it out. All right, great. Thank you. So I'm going to spend the next 3 minutes convincing you all why, it seems to have a mind of its own, convincing you all why we can do cosmology using high resolution X-ray spectroscopy. Okay, and this all hinges on the fact that galaxy clusters are really good probes of cosmology, and that is because the conditions in the early universe determine to a large extent the masses that you see in clusters in the current day, because little primordial fluctuations are the things that turned into those clusters, and those fluctuations were driven by cosmology. So if we're able to measure the mass distributions of clusters across cosmic time, we can trace back to this original cosmology and infer the cosmological parameters. Now, we need to measure the masses of the clusters. It turns out measuring masses of a cluster in X-rays is very efficient. The intercluster medium is just a big ball of hot gas. If you measure the density, you measure the temperature, basically you measure the pressure of that ball of hot gas, and you assume it's in hydrostatic equilibrium, then you can estimate the mass of the halo in which the ball is sitting. Of course, that is a big assumption, assuming it's in hydrostatic equilibrium. And there are lots of non-thermal effects that can violate that assumption. In particular, turbulence can. So one important question in cosmology using galaxy clusters is how important is turbulence in providing non-thermal pressure support to this ball of gas? So we have to date exactly one direct measurement of the turbulent velocity in the intracluster medium for the Perseus cluster, which we've seen a couple times so far. Hitomi measured this to be about 150 kilometers per second. And that was surprising, mostly because it's very quiescent. It's a very low turbulence, despite all of the features that you can see in this image. There's a lot of AGN feedback happening. But we're actually, for the purposes of cosmology, much more interested in what's going on way outside of the core of the cluster, where effects from feedback are not so important. And so what we really want to do is we want to measure the turbulent velocity hundreds or even thousands of kiloparsecs out from the center. where you're seeing much more pristine material in the ICM. And so a goal for a XRISM PV observation is to do just this, to measure the turbulent velocity far away from the core in a relaxed galaxy cluster. And we expect that turbulent velocity, or the non-thermal pressure support, to be on the order of 5 to 20% from simulations. That should produce, if it's all due to turbulence, a turbulent velocity greater than 250 kilometers per second. So this is what we plan to do with a PV observation of Abell 2029. We're not going to do it with Perseus to begin with. Abell 2029 is hot, it's very relaxed, and it's at a distance where R2500 or 600 kiloparsecs is close enough that we can cover this with just a couple of resolve pointings. So this is an XMM image of it, shows you the resolve pointing out at R2500. That is a simulated spectrum. And what we want to do is measure the width of the helium-like and hydrogen-like iron K lines. This spectrum is simulated for 250 kiloseconds, which is the length of our observation. So you can see it is not the highest statistic spectrum you'll ever see. In addition, we have to worry about emissions scattered from other bright parts of the cluster into this region. So this observation will really help to demonstrate, first of all, how good XRISM is at observing very faint diffuse emission. And secondly, how good our understanding of the PSF is, so that we can remove the effects of scattering from other bright regions. Basically, how good of an imaging spectrometer it is. So my time is up. I do want to just point out that I have a nice poster about this 3 floors above here, right outside my office, very conveniently located. So if you're interested in reading more about this at a break, head on up there, and maybe I'll be in my office, which is that open door right there. Thank you very much.
Thank you. Next talk. Try again with
share sound. Here we go. So, a galaxy cluster, largest gravitationally bound object in the universe. It has 2 categories, mainly. Hi, I'm Majidul. I'm here to present my recent work on spiral-like features in galaxy cluster driven by AG and jet feedback. So, a galaxy cluster, largest gravitationally bound object in the universe. It has 2 categories, mainly relaxed cluster and disturbed cluster. This is one of the example of relaxed cluster. If you see, it is very smooth. However, if we subtract average profile from them, we got very interesting spiral-like features. Main motivation of this work is that current understanding says that merger with non-zero impact parameter can trigger spiral-like features. However, merger events are less common in cool core cluster than non-cool core cluster. However, a significant fraction of cool core cluster hosts AGN at the center of the cluster. Therefore, effect of AGN feedback activities in cool core cluster need to be investigated carefully in different projection angles. Therefore, we simulate AGN jet feedback using flash code with adaptive mesh refinement and technique, and for each epoch we further simulate to have a mock Chandra X-ray observation using PyXM, and similar to the previous method, we subtracted average profile and we got similar spiral-like features using simulated mock Chandra X-ray observations, and it is visible over 90-degree wide angles. So main distinguishable features between merger scenario and AGN jet scenario can be investigated using telescope like XRISM. using Doppler shift of X-ray lines, we can have these maps. And main difference is that for AGNJ simulations, only center will have a larger bulk velocity, and for turbulent velocity only for 2Ks merger simulation will have larger turbulent velocity with respect to AGNZ simulations. So thank you.
Thank you, Majidul. And I remind you that you can always post questions on the Slack channel if you have questions. Next flash talk is from Tomáš about cavity detection tool. And right.
Yeah. Okay, so hello everyone. Thank you for the opportunity to speak here. My name is Tomáš Plšek. I'm a second-year PhD student at Masaryk University in Brno, Czech Republic. And today I would like to introduce you a cavity detection tool, a machine learning approach to detect X-ray cavities from raw Chandra images. Sorry for being slightly off topic. This is purely image-based approach, but it's well suited for Chandra, and I hope it might be of interest for some of you who are studying X-ray cavities. Okay, so very quickly about X-ray cavities. So they are basically void bubbles inflated into hot atmospheres of massive early-type galaxies and galaxy clusters. And they were inflated by relativistic jets during the so-called radiomechanical AGN feedback. And they are pretty well probes of radiomechanical AGN feedback, because for many galaxies, they represent the only remnant left over after previous AGN activity. And we can probe the radiomechanical feedback using them, because when we estimate the volumes and combine it with the surrounding thermal pressure, which we get from the spatially resolved spectral analysis, we can get the total energy required for their inflation. Unfortunately, the way the sizes of cavities are estimated now is that we are basically manually drawing ellipses over those cavities in the S9, which wouldn't be such a problem if all observations of galaxies looked like NGC 5814, but most galaxies actually look like this. This is NGC 4649, and by eye, you cannot even tell whether there are cavities on this image or not. But this looks like a nice problem for a machine learning algorithm. So we took an inception-like convolutional neural network. We trained it with purely simulated images, and we combined it with a DB-scan clustering algorithm to produce this cavity detection tool pipeline. And it works like this. On the input, there is a cropped raw Chandra image, possibly with filled-in point sources. It's processed by the convolutional neural network, and on the output of the convolutional neural network, there is a pixel-wise prediction with basically each pixel represents something like a probability that this particular pixel is a part of a cavity. And this pixel-wise prediction is then decomposed into individual cavities using the DB-scan clustering algorithm. And we applied it also on real Chandra images with previously known X-ray cavities, and we detected 93 out of 97 previously known X-ray cavities. And on top of this, we also discovered 7 new cavity pairs and 8 new cavity pair candidates. Okay, and this is one of the candidates. And in the following seconds, I will very briefly show you how you can use this cavity detection tool. So first of all, you can load the raw model using Keras. We have also built a web interface, which I don't have too much time to show right now. We also packed the whole pipeline into a Python package, which can be easily installed using pip install pycadet. And alongside with this Python package, you also get a DS9 plugin, which I'm going to show right now. So here I have, sorry for the delay. Here I have an image of Galaxy NGC 4649, and I have this pycadet plugin installed. I'm gonna make a box region. something like this, centered at the center of the galaxy, and focusing on the center where the cavities possibly are located. I'm going to click analysis and then cadet, and now it's going to take like tens of seconds. It's going to process this part of the image, it's going to produce the pixel-wise prediction, and then decompose it into individual X-ray cavities. It's a little slower because of the zoom right now. Sorry about that. Okay. At least it's not a blue death, like with Microsoft. Okay, sorry for that. I'm going to try again. Oh yeah, there it is. Okay, so this is the pixel-wise prediction, and there it is decomposed into individual cavities. And what you also get is this table with parameters of individual cavities. So cavity 1 has area of this many arc seconds, and cavity 2 this area and this volume. Okay, thank you for your attention. Thank you.
The next flash talk is by Francois. Never mind. About and I guess it's recorded.
I'm really sorry that I cannot be here with you today to tell you about this very exciting discovery, which I would like to talk right now, which is diffuse inverse-Compton emission in a galaxy group. And we think that this is actually the first time that we have robustly detected such an emission in a system of galaxies. So the first question here I would like to address is, why is detecting diffuse inverse-Compton emission important in galaxy clusters? And the answer is because of magnetic fields, because we don't really know the volume average magnetic fields in clusters, and these numbers are extremely important for especially for cosmological simulations and to better understand the clusters' magnetic fields in general. And what we can do is, in a very unbiased way, is actually isolate these magnetic fields measurements just by looking at inverse-Compton emission that sometimes you can see in galaxy clusters, because you may have a population of relativistic electrons, which also emit radio at radio wavelength here. And so if you are able to isolate this non-thermal component here from the thermal component, and if you just divide this flux by the flux of the radio synchrotron emission, you have a direct measurement of the magnetic field here. Of course, it's actually very difficult to do that because the thermal component is usually very, very hot. We're talking usually about massive mergers here. And what we would like to do is to do exactly the same with a galaxy group, where the emission is actually much cooler, and then you can really separate the two components here. And the good news is that we were able to do that by looking at a very poor galaxy group called MRC 0116+111. Here are the radio contours. So this group has an extremely bright, extremely diffuse radio emission here. And if you look at a spectrum of XMM Newton with very, very deep observations, you are actually able to isolate the two components, and you can definitely detect here a radio tail whose slope matches exactly the expectations if you're thinking of inverse-Compton emission. The second hint is that if you separate the images of the soft band, so presumably tracing the thermal emission, and the hard band, presumably tracing the non-thermal emission, you see very different morphologies. And where you have a cavity here in the soft band with a peak of radio emission, you do also have a peak of hard X-ray emission, which is again what we expect from inverse-Compton in the inverse-Compton scenario. These measurements have been also made very robust towards a lot of systematic effects here. So we believe that these results are very robust here. And the constraint we get on the magnetic field is about 2 microgauss, which is basically what you would expect for clusters. But for groups, this is actually 1 or 2 orders of magnitude higher than what we find in simulations. So this is actually a very interesting number, which hopefully will be able to constrain better future simulations. We're also very excited to see new star data coming here, which have been already observed. And I think it's very important to have high resolution spectroscopy here to better isolate the thermal from the non-thermal component here even more robustly and better understand and better measure magnetic fields in clusters. And I will stop here. Thank you very much.
Thank you, Francois. Okay. In the hot circumgalactic media of nearby simulated disk galaxies with high resolution X-ray spectroscopy.
Evidently, the microphone wanted to issue a warning, so. Okay, we get rid of the echo? Okay, good. All right, so thank you to the organizers for allowing me to contribute this talk. I'm going to be talking about measuring velocities of different kinds in the hot circumgalactic medium of disk galaxies with high resolution X-ray spectroscopy with LEM. This is based on a recent paper that's been submitted to AppJ and was archived with a number of these collaborators and a whole bunch of other folks. So we've already heard a little bit about the circumgalactic medium this morning, but it's the multi-phase gas medium filling the halos of galaxies. So if you look at this picture, you're seeing projections of the stars and various gas phases from a galaxy from illustrious TNG 50. So you see the spiral shape in the center. The circle gives you R200C. And then for this particular galaxy, anyway, you can see you have cold gas, warm gas by those temperature definitions, and then you have this volume filling hot gas, which is true for galaxies, roughly Milky Way mass and above. And this is the repository of gas falling into the halo from the intergalactic medium, but also expelled from the galaxy via feedback from AGN and the stars, and everything is recycling in and out of this medium. So today I want to focus on velocities, and you obviously this is an interesting concept drawing from this nice review by Forcher, Giguere, and O in earlier this year, and you can sort of just decompose the different kinds of velocities into outflows. We have feedback, from AGN, supernova, and starbursts. You have inflows from cosmological accretion. There's some questions about whether or not the inflow stays hot, or if you have precipitation of the hot gas down into cold droplets, and that's how they inflow into the galaxy. But then also we expect the CGM to have some angular momentum, and so as it falls in, you might expect it to have some rotation. And of course, we also expect this medium to be turbulent to a certain extent, although I'm not going to talk about that very much this morning. So as we've seen already, as Irina and others have described, and the whole point of this workshop is that high spectral resolution is very necessary. So we can't measure velocities or even see the hot CGM except on the innermost parts and massive nearby galaxies where we can. But if you want to see it out further, and if you want to actually map the CGM in different thermodynamic and kinematic components, you need high resolution X-ray spectroscopy. And the reason, which you've already heard, of course, is that the Milky Way hot CGM, which you can see, there's a pointer here, in these blue lines here, emits at the same atomic transitions as the CGM in external galaxies, and it's much brighter. And so this is an example of an external galaxy. We've simulated the X-ray emission. This is actually very similar to a plot that Irina showed, but here is what this would look like in CCD resolution, so you can see some of it. But if you actually want to map the CGM at different temperatures and in different phases, you need to look at these different emission lines. So here we have oxygen 7, oxygen 8, and iron 17. And if the source is cosmologically redshifted, this particular galaxy is at Z of 0.01, then you can actually see the lines from the external galaxy next to the Milky Way emission lines. So you've already heard from a few different people about line emission and mapping. Here are the main characteristics. I'm not going to go into a lot of detail. Again, except to say that for this work, we focused on the inner array of 7 arc minutes, which will have roughly 1 EV spectral resolution, at least in the current mission design. And so what we've done is that we've taken a sample of 6 galaxies from the illustrious TNG50 simulation, which is part of this Milky Way M31-like sample in Plšek et al. 2021. And these galaxies all are disk galaxies that exhibit cavities that look like the Fermi/e-Rosita bubbles seen in our own galaxy. And what we've done is that we've used the PyXim code to simulate the X-ray emission from the galaxies, and we've used the SOX code to pass the emission through an instrument model for LEM. And if you want more details on that software, we can talk about it during the coffee break. First, let's just look at let's not deal with mock observations. Let's just look at what these things look like from just projected quantities from the simulation. So this is looking at one particular disk galaxy from the sample edge on. So these are the stars over here. This is the projected X-ray surface brightness in the 0.5 to 1 keV band. So you can see that there's these AGN-driven outflows up and away from the disk in both directions. This is the emission-weighted temperature. So you can see, not surprisingly, that these winds are hot and they heat up the gas. But then you can also see this is the emission-weighted line shift. So the first moment of the velocity distribution, you can see that there is a blue shift here and a red shift here, conveniently color-coded. And what you're actually seeing here in this edge-on view is actually the rotation of the hot component of the CGM. And this over here is that you're actually seeing the projected line width of the line. So you can see that, roughly speaking, the areas where you have the bubbles is and the outflows is where you have more, structure along the line of sight to produce line widths. So what happens if we take this galaxy and we rotate our line of sight? So now we're inclined 45 degrees. So now you can see a bit more of the disk. You can see the outflows still away from the disk, both in surface brightness and temperature. And now what you see is that you're actually seeing the oppositely directed velocities from the outflows in either direction that are superimposed upon the rotation curve, which is why you have this, you have the outflows going in either direction, but you also have this tilt. This is because you have this complex superposition of both the effects of the rotation and the outflows. And then what if we look at it just straight down onto the face of the galaxy? Well, then things get really messy because on average, if you average this all together, what we're seeing is is roughly like 0 line shift. But of course, you can actually see that in the paper that it averages out to 0 by construction, at least, of course, because we're looking in the rest frame of the galaxy. But also, that's on smaller scales. Of course, everything is very patchy and turbulent. But let's do some averaging. Let's take a cylinder that's aligned with the galactic disk, and let's look at some of the properties of these flows. So if we look at the radial outflows here, the radial velocity direction here in these panels, what you can see is that on average, close to the vertical axis, the minor axis perpendicular to the disk, you can see these outflows, which are colored in red. They're fast. They're up to 400, 500, even faster kilometers per second in places. And if you look in the closer to the disk, you can see a slower inflow, about around 100, 150 kilometers per second. So a lot, and then if you look over in the azimuthal direction, you can see that this is actually the CGM rotation that I showed you in the map. And here's another one of the galaxies from our sample that has a very similar structure. By the way, the left panels are showing hot gas, which is about 5 times 10 to the 5 Kelvin and hotter, and then the right subpanels are showing basically everything else, which is sweeping, of course, a lot under the rug, but I am focusing on X-rays here. So a lot of the galaxies look like this. Some of them don't quite look like that. Some of them look more disrupted and don't necessarily have the same coherent flows. But for the ones that do look like this, you can imagine that if you were to observe them with a microcalorimeter like LEM, if you have a model like this, where you have inflows, outflows, and rotation, then if you view them edge on, you might want to measure that rotation curve by carving up your, by taking spectra in little tiny rectangular wedges here, or if you're looking down face on, you might want to look at everything in annulus. It's just annuli, rather, as suggested by the geometry. So we've created these mock event files. These are actually mock LEM images in the oxygenate line. I'm showing you the regions that we've chosen to extract spectra. So this is first on edge on, and the blue line is the fits to the line shift from the spectra, and the orange line is the prediction from the simulation on the left, and on the right you have the same thing for the velocity dispersion. So we can actually measure the rotation curve of the hot CGM in the disk galaxy edge on using LEM, and although not the same kind of accuracy, we can also measure the velocity dispersion along that line of sight as well. And finally, if we look down face on, we get more complicated, because what we're doing is we're looking down along these outflows coming out in opposite directions like this, but we're also looking into this really complex, like multi-phase thing. And so what we do here is that we actually have to do like multi-component models with different velocities and different temperatures. We're essentially fitting different thermal components, and you can see that like we've identified, depending on like the angular region, there's up to 3 different temperature components which have different velocities and even different velocity dispersions. And not surprisingly, from our simulations, the hottest gas here, which you can see is around 8 times 10 to the 6 Kelvin, or roughly 0.8 keV or so, that actually has the highest velocity dispersions, which is exactly what you expect, because that gas is the hot gas that's moving in opposite directions, and you're just seeing those oppositely directed flows producing that velocity dispersion. And finally, we can make maps. So on the left, you see the edge on. These left panels here are actually projections direct from the simulation, no instrumental effects here. But this is actually the LEM simulation, and this is the fit that to this event file from the LEM simulation to produce a velocity map. So you can recover the rotation curve, and you can actually map the velocity distribution. And then if you do the same thing for the inclined galaxy, you see that tilted velocity distribution. So you can not only get velocities of particular parts of the CGM along sight lines, you can actually map it over a large region. So with that, I'll put up summary and take any questions.
Thank you, John. You're perfect on time.
Okay, good.
Questions?
In the TNG50 simulations, how much of the energy input is from supernovae and how much is from AGN feedback typically?
So in these size galaxies, most of the feedback is from the supermassive black hole and the Milky Way mass and above. Now, in these simulations, of course, the feedback implementations are very tricky. They're subgrid, and so basically you are launching winds by the supermassive black hole is basically influencing the gas cells around it by just giving them little. At least in this particular mode, just giving them little kicks in random directions, actually. But in the case of these galaxies, the dominant feedback is the AGN feedback.
Perhaps I missed it, but so you have a 3 temperature component gas in these.
That's correct. Yes.
Oh. And I guess this is from simulations. My question is, how do you disentangle the 3 components in the data? Because the lines are superimposed, I guess, or are they shifted in velocity that much that you can resolve them?
So this is a very good question for Anna, who did this work, this part of this work.
the kind of spectra we have from LEM, like 1 eV, very high. This is like a 1 megasecond kind of exposure. So you have lots of photons. So basically, because of you have so many different lines, you start with like carbon through nitrogen, you have oxygen, you have iron. So basically, you just have enough statistical power to, by the different temperatures, so contributions to those different fluxes, and also line widths, which you can see are also very critical. So fixing or tying your line widths and fits between different components would not let you disentangle this. So basically, the spectra are so good, and they're actually shown in the paper for every single component. So you can go and look at them basically. But it's just the LEM quality spectra, it's just unimaginable. Like, you can do so much. You should be so excited.
Time for the last quick question.
So when you look at the inner regions of these galaxies, do you account for the absorption by the cool gas in the galaxy?
So not in this paper.
Okay.
No, but that's obviously something definitely be a good thing to look at. So
Thanks again, John.
Okay.
The next speaker is Andy Fabian. And I lost him. Okay. Which we talk about heat and cooling flows in cluster and groups of galaxies, and they will be remote.
Oh, that's probably a good idea. Yeah.
Andy, we cannot hear you.
I've unmuted now. Is that okay?
Now, yeah. Please go on.
Okay, thanks for the opportunity to talk about cooling flows in clusters of galaxies. I'm starting out with a beautiful picture, a Hubble picture of the center of the Centaurus cluster, and the details you can see there are going to be important later. We've already done 3 papers on this issue. If you want to catch up with it, they're all hidden cooling flows in the title. So, oh dear, it's not, there we are. Basically, cool core clusters are ones where the core of the cluster is cooler than the surroundings. And as you go further in, so it gets cooler and cooler. And in order to maintain the pressure to support the weight above, the density rises. And so we get this enormous surface brightness spike that you can see in the centers of them. And notice this is Abel 478, and this is plus or minus 1 megaparsec. So these are big effects. And the coma cluster, which is a non-cool core cluster, has essentially an isothermal flux, isothermal temperature. And so therefore, it just has this small bump in the middle. So we're looking at this part of the cluster, the brightest part of the cluster. And what one can do is to measure the cooling time of that gas as a function of radius, which is what you can see here done for many clusters. And basically the cooling time is the time in which it will lose its thermal energy by emitting the X-rays we see. And you can see the cooling time of much of this gas drops below 10 gigayears down right at the bottom left. It's going down to 10 to the 7 years. And they all look very similar in these cool clusters and have a similar profile. And it all looks pretty much the same. You can't see breaks or anything like that. So that's what we're going to talk about. And back about just over 20 years ago, when we got the first RGS, first high resolution X-ray spectra of these regions, a big problem emerged, because if you look at the spectra, and the red is showing you the model and the black is showing the data, the model for a cooling flow where the gas is cooling down, losing its energy, and so you can therefore have it in a continuous cooling flow going down to below X-ray emitting temperatures, would predict very strong iron 17 lines. And you can see little in the data in this cool core cluster. And the simplistic interpretation of the data basically implied that the gas was not cooling very much. It was only cooling down to a half or a third of the outer temperature, and any mass cooling rates were much smaller, less than 10% of what was otherwise in earlier work, including from my own, it certainly was reduced by a factor of 10 or more. Now, what was thought to be happening, and this is work from Chandra, is here's this wonderful picture of the Perseus cluster. You've got all these cavities and action from the central AGN. This is AGN feedback. It's feeding energy into the intracluster medium. Basically, what's happening is the cooling is being stifled. And so that was thought to be what was going on in these clusters. But I became a bit and have been concerned about this because it seems to happen in all core clusters that basically once you get to temperatures, you follow the gas down towards 1 keV, and then it just seems to disappear, as you can see with the cooling rates in this cluster here. And everything seems very gentle and continuous, but it all seems like fine tuning. How does the heating know to combat the cooling even when the cooling is very small? And just why don't we get, say, no gas at all, or maybe enormous amounts of gas? So it seemed to me like fine tuning. And most X-ray astronomers, when told there's a lack of material observed below 1 keV, most of you would say there's obviously X-ray absorption. And can this explain what's going on? Now, over 30 years ago, with Ginger data, Einstein solid-state spectrometer data, and later with ASCA CCD data, we did think we were seeing large amounts of absorbing material in cooling flows. This was not a very popular approach. And one of the problems is that how do you get so much gas down there, and what is the gas and what's it doing? If you include the absorption of soft X-rays by cold gas, but allow it to occupy the same region as the cooling glass, you can have a multi-layer intrinsic absorption model, which we used back in 1997. That's Steve Allen and I and others. Then basically it fits much better. And essentially what you have to do is to conserve energy. So the energy from the gas cooling below 1 keV has to come out somewhere. And so we assume it comes out in the far infrared and the UVA, all the other wave bands. So the model I'm going to use here is not of a cool core with a big shield in front of it of absorbing material. I'm making the absorbing material be intimately mixed with the emitting gas. So the cold gas, hot gas are intermixed. And a very simple way to do that is just, as you can see up there with the red and blue indicating cooling flow and obscuring material. And that makes a geometric series, which you can then get to give this equation, where that's what is transmitted and observed based on compared to what is emitted. And this is the total column density through that region. And down on the bottom right, you can see where this is the emission plotted against wavelength. You can see this is what just a constant temperature does. The black one is what a cooling flow that's truncated at 1 keV would look like. And this is what one of those hidden cooling flows, which is what I'm going to call this, looks like. And you can see how it all drops away as the wavelength increases at low energy. And in a sense, what we detect isn't much different from a truncated cooling flow. I've been looking at RGS data and working with them for the last couple of years on this. And if we go to the Centaurus cluster, where I'm going to show you a much better spectrum in a few minutes, but it looks rather messy, but you can see emission lines in it. There's oxygen 8 and the iron 17 lines and so forth. But when I do fit this model, I can get that the mass cooling rate in this object is 15 solar masses per year. I can fit it to the Perseus cluster and I get 80 solar masses per year, plus or minus 50 or so. Where does the energy comes out? It comes out in the far infrared. Herschel has looked at the Centaurus cluster and Perseus cluster. In the Perseus cluster, it's resolved the far infrared emission. It coincides with right in the core of the cluster there. And the Centaurus, you can see this bump, which is, it looks like a black putty bump. That is the emission from dust in the center. And so that's where I think that this hidden cooling flow emission is coming out. A big issue, and this is for most astronomers, is do you not accumulate too much cold gas? And the answer is maybe. In a gigayear, you get 10 to the 10 solar masses in Centaurus and 10 to the 11 in Perseus. But what exactly is too much gas? There's a lot of gas in the cores of clusters anyway, and all you're doing is rearranging it. There is much cold gas observed in many of them, particularly in molecular hydrogen, in CO observations show that, but they don't show much more than 10 to the 11 solar masses. So we would have a struggle making the Perseus cluster have a lifetime of say 5 gigayears or something. A speculation we have is that maybe the gas continues to cool down towards the microwave background temperature, and you get lots of ultra cold clouds. I'll show you a plot about that in a minute. Also, that the bubbling in these clusters destroys clouds and drags them outwards, and that can maybe regulate the cool gas mass. Another interesting possibility that was introduced by Mike Jura back in 1977, but I've been looking at it ever since, is the very high gas pressure in these objects, which is 10 to the 4 times higher than our interstellar medium, that lowers the James mass. And maybe we get a bottom heavy IMF. In other words, you form lots of low mass stars. Here we have the Perseus cluster where you can see lots of H alpha emission, lots of molecular gas. It's 5 times 10 to the 10 solar masses. This is just a work from Gary Furlan showing that the gas can go right down to the microwave background temperature. And the cooling time of that cold gas is actually only 30 years. So you have to do something continuously to not have ultra cold clouds. Here are going through a bunch of cool core groups and clusters, nearby ones. And if you look at them with HST images right in the core, it's quite clear there's lots of patchy absorption. They're full of absorption in the cores. So there's no doubt there's absorption taking place. So if you're going to have emission from the same region in X-rays, it's going to be absorbed. This is just showing you the ratios of the hidden cooling flow rates to the imaging rates. We can also grow the black hole. I won't go into that in any detail. Here I now have got a spectrum of Centaurus, which is neater, and it's around 16 solar masses per year is the best fit here. And just to show you, if I now switch off the cooling, this is what it would look like if there was no absorption in the cluster. The absorption in the cluster has made it go from that to, made it to go to that. Looking again at Centaurus, right in at the center, there you can see a lot of absorbing material. And if you go and look I've tweaked the image now, and you can see it's distributed as well as these strings of cold, dusty gas. If we go out to redshift 0.35, there's some beautiful clusters out there with really spectacular large emission regions. This is H alpha, Lyman alpha, and so forth. But they are also core clusters with cooling rates of over 1,000 solar masses per year. We also see in some, this is work by Tom Rose and others, you can see absorption against the nucleus. So I'm looking forward to what XRISM's going to say about these objects. Also, there's Athena, and this is what, of course, we're all waiting for, is the probes in the 2030s. My summary is that intracluster medium is cooling below 10 million K, mostly hidden by intrinsic absorption. The mass cooling rates are much bigger than the unabsorbed estimates, but they're still less than if there was no AGN feedback at all. AGN feedback does work, reducing it by a factor of 2 or 3, but not by a factor of 100. Most of the absorbed energy emerges in the far infrared. Ultra cold clouds can exist, and low mass star formation seems to me to be a good bet. The inner few kiloparsecs of cool cores are very complex and multi-phase. I'll just say it's very difficult to simulate this, and actually no simulations I know of include any absorption. And some of the substellar objects may be swallowed whole by the central black hole, and that may be why the BCG black holes are the most massive in the universe. All models and interpretation I can find require cold absorption in these regions. Thank you.
Thank you, Andy. Question for Andy.
Hi, Andy. This is Fabrizio.
Hi.
So this is essentially the escape probability. The cross section you use is the for a cold gas, neutral gas. Is that
Yes,
right?
absolutely.
Okay. So I understand, and I actually like the idea, but the problem is that the contrast between lines and continuum should stay the same. I mean, you can lower both, but the lines should still stick above the continuum.
Yeah, they do.
And you should see them in the spectrum, no?
Yeah, you do. Sorry to be boring. Let's just go back to Centaurus there. You can see the emission lines. In this, here it is, the black component there is the absorbed cooling flow component. And this is what we see in the core of the Centaurus cluster. So there are the two iron 17 lines there and there. The oxygen 8 lines are there and there. And there's lines from iron 18 and so forth there, and the other rest of the iron L complex here. So you see the lines, and of course they're being absorbed as well as the continuum.
Okay.
Next question.
So Andy, this is Daniel Wan. So
Daniel?
I was wondering about the lack of oxygen 7, which probably is because the cooling times get too short for the lower temperature.
There will be oxygen 7. It's just going to be even more absorbed.
Okay.
It is on the right there. You're starting to see it, but the trouble is the absorption. It's got a column of 1.5 times 10 to the 22. That's the total column. It wipes out oxygen 7.
But this is a little fine tuning. You need to hide all the cooler gas behind the absorber.
Well, I think that's what you would get. Yes.
Mm.
Okay, and just think about, you have cooling gas. It cools down to make cold gas, but imagine it now. You introduce mild turbulence. So you mess the whole thing up. So the cooling gas is mixed up with the cold gas that's been made after the cooling. And that's essentially what is going on in the centers of these objects, in my view. There is work, and Ciro Pinto led a paper about oxygen 7 in these objects. And that if you go at it carefully, you can find small traces, which of course would come from gas which happens to be on the cool gas that happens to be on the outside of this big region in the center. So I have no problem with lack of oxygen 7 in the spectrum.
Thank you, Andy. We have to move on because coffee is waiting for us.
Of course, enjoy the coffee.
Thank you, Andy, but we can move the discussion on Slack. Thanks a lot.
Thank you.